Now, let us look at what are the different wavelengths that are present in the electromagnetic radiation. So, over here in this picture, some of the wavelengths are shown. They are expressed in meters here, and on the bottom axis, their corresponding frequencies are shown. So, the velocity of the EM, all these EM waves are the same. They are in vacuum, they are the same as the speed of light. 3 times 10 to the power 8 meter per second. So if their wavelength is larger, then their frequency must be smaller because V equals F lambda. So just to compare the length scale as of the wavelengths, various known objects are shown also. So if we look at radio waves, they can be about like say of the order of like meters to kilometers, for example. Their wavelengths are of the same size, for example, as those of buildings, the lengths of the heights of buildings. Then if we look at microwave, they have slightly shorter wavelengths, and the size of people maybe few meters. Infrared is even shorter. In this case, the size of ants may be small insects. And then we come to visible light. So this is even smaller. This has even smaller wavelength. And then we go out of the visible range again, ultraviolet spectrum, then X-ray spectrum. X-rays have like wavelengths that are typically of the size of atoms, like nanometers or angstroms. And then even if we go to the far right of this spectrum, we see gamma rays, which are typically like which emerge from atomic nuclei, and they have very small size of the order of 10 to the power minus 12, for example, meters. And also like their frequencies are very large, like almost 10 to the power 20 hertz, for example. Okay, so let us look at some of these electromagnetic radiations in detail. So before that, it is important to note the following points. So all of these wavelengths, they travel at the same velocity in vacuum. The speed is 3 times 10 to the power 8 meter per second. And all the EM waves are called light. I mean, so there is no distinction between light and any of these other components, for example, X-rays. All are just electromagnetic waves. So they differ in frequency and wavelength to maintain the constancy of the speed of light, as we have seen already. And all of these waves consist of oscillating electric and magnetic fields. Let's look at gamma rays. Their wavelengths are of the order of 10 to the power minus 10 meters to 10 to the power minus 14 meters. And they are emitted by radioactive nuclei. And they can penetrate thick walls even and can cause damage. For example, if living tissues are exposed to these rays, they can be damaged. These rays are highly penetrating. So let us look at radio waves, which is at the other end of the spectrum basically, and their wavelength is very large. It could be of the order of 10 to the power 4 meters. Of the order of kilometers, for example, or it could be even 1 meter or a bit less. And this is used in radio and television communications, so these are very important in terms of applications. And then there's microwaves. They have wavelengths that are about 0.3 meter to 10 to the power minus 4 meter. And these are well suited for radar systems, for radar detection. And these are also used in the ovens where we warm our food or cook our food. Infrared waves. This has slightly smaller wavelength, slightly larger wavelength than the visible wavelength, visible light. So their wavelengths are of the order of 10 to the power minus 3 or 10 to the power minus 7 meters. And they are often called heat waves, but that is incorrect. They are not actually heat waves. They are just electromagnetic waves that appear basically, that are just below the red light basically, and they are emitted also by hot objects and molecules. So that's why incorrectly sometimes they are called heat waves. And these are readily absorbed by most materials. And visible light is the part of the EM spectrum that our eyes can detect. And our eyes are most sensitive to about like 5 times 10 to the power minus 7 meter wavelengths, which is in the yellow to green regime. And over here you see the visible spectra of the visible light that has different colors. The colors are basically based on the wavelengths. So violet is on the left, that has the shortest wavelength, and the red is on the right, that has about 700 nanometer wavelengths, and the other colors lie somewhere in between. So ultraviolet light covers about 4 times 10 to the power minus 7 meter to about 10 to the power minus 10 meter wavelengths. The sun emits a lot of ultraviolet or UV light. Then let us look at X-rays, which are very important in medical equipments, because I mean they can penetrate our bones, our body, and obtain images of our bones and internal organs. So their wavelengths are in the range of 10 to the power minus 8 to 10 to the power minus 12 meter. And these are emitted by acceleration of high energy electrons, which could strike a metal target, and then this radiation is emitted as a result. So over here you see some images of a nebula called Crab Nebula, and these images are acquired by collecting different wavelengths of light. For example, and the first picture is made from collecting radio wave through a telescope, and then the bottom left picture is from ultraviolet radiation, collecting ultraviolet radiation. So based on their the wavelengths, the collected wavelengths, the nebula appears to be of different form basically. And so what is the model of light? We have already talked about that. Light is composed of oscillating electric and magnetic fields. So these are perpendicular to each other, and these are self-sustaining field. So an oscillating electric field is generating an oscillating magnetic field, and the oscillating magnetic field is in turn generating the oscillating electric field again as the wave is propagating forward. The direction of propagation is perpendicular to the planes where these E and B fields are oscillating. So what is polarization? So waves can oscillate in multiple planes, but it is possible to restrict them to single planes of oscillation. When this is done, the waves are called polarized EM waves. So over here you see that electric and magnetic fields are oscillating perpendicular to each other. The oscillation is shown by the double-headed arrow. But we can restrict the oscillation only in one plane also, in this case the E field. So this becomes a polarized EM wave when this happens. So unpolarized light contains waves that are oscillating in multiple planes and are randomly oriented basically. The electric and magnetic fields do not lie in a single plane. They are spread out over multiple planes, and they are randomly oriented as a result. Now let us take an unpolarized E field. The arrows here are showing that that there are different planes involved of oscillation. All directions are possible. The resultant EM wave is a superposition of all these different wave components. But over here we show a polarized wave. It is linearly polarized. That means only one single plane exists. It is polarized in only one direction. The E field here only vibrates up and down in this case. The plane formed by E and the direction of propagation is called the plane of polarization. So the wave is propagating in another direction. So there is a plane you can define that plane based on the polarization direction and the propagation direction, and that is called the plane of polarization of the wave. Polarization can be achieved by various methods. For example, you can remove all the other components of the wave and have only, from an unpolarized wave, you can remove all the other components and only have the linearly polarized beam. And this can be achieved by various techniques. It can be reflection or double refraction or scattering or even selective absorption. And the figure here shows one way to polarize a wave. So an unpolarized light ray is coming, so the arrows are indicating all different directions. These are all mixed together, and we apply a filter, which is basically a vertical plane, and at the end, like when the wave passes through this filter, only one component exists, the component that is oscillating vertically. The light ray that was polarized in this direction, vertical polarization, that can emerge out of this filter. So this is how we can polarize the light wave.